Hello everyone, I'm Bingjo. Welcome back to another video. So in this video, we're gonna go into the this video is the second video of chapter 4, and I had decided to split the original plan into two more videos, which means this will be one video and there will be another last video for chapter 4, so that it won't be too long and too condensed in one video. So let's go with the agenda for the video today. Okay, so the first thing we're gonna do today is about rotational symmetry. Rotational symmetry and line symmetry. Yeah, just to double confirm the name. And excuse my spelling if it's wrong. Okay, and then after that, we'll be looking at angles which are on a parallel lines. Yeah, angles within parallel lines. Okay, just to give you a rough guide, there will be three of them. Okay, number one is the alternate. B is complementary. This is ugly. Complementary, and the last one is co-interior. Okay, and after that we'll be learning the last thing for today. Why is this actually drawing? I thought the right side should be no. Okay, and then the last thing for today will be the first one will be interior and exterior angles. Okay, so if all these things do not hit you don't understand any of this, please continue to watch this video until the end. All right, if you already know anything that if you already know everything that is going to be covered in this video, please do not waste your time. Go and study or go to the other videos that you are not confident of. Okay, so yeah, without further ado, let's go to the I actually don't understand why this is okay, I think I'm gonna just move like this. Okay, so without further ado, let's go to our first agenda for today, which is rotational symmetry. Okay, so number one is what is rotational symmetry? So by the name it suggests it's the symmetry when you rotate a shape. Okay, so for example, I'm gonna draw a square. Okay, let me write the title up there first. Okay, rotational symmetry. Okay, so if I'm gonna draw a shape, let's say a square, which probably doesn't look like a square, but let's assume it's a square. Okay, and then I'm gonna ask how many rotational symmetry are there in a square. Okay, and the answer will be 4. All right, just say there are 4 rotational symmetry in this square. But how do we get the answer 4? Okay, and how do we find a rotational symmetry? Number one is you are gonna rotate the shape. Okay, so if I'm gonna add something like a dot here, so your first rotation will go to the first 90 degrees rotate until you get the same order, right? So let's say you have a square which is flat on the top and then 2 by the side. You will turn the square until you get the exact same one as the original. If you are going to ignore the dot here, okay, the dot is just to show you how many rotational symmetry are there when we rotate the square. Okay, so from this you rotate until you get another flat line on top. Okay, this is one rotational symmetry. Okay, then you will continue, all right, to rotate the square until you get another flat line on top. Okay, so from the original square, you can see the dot is already at the bottom now, so you already turned the square 180 degrees, and this gives the same shape as the original one. So you will have 2 rotational symmetry. Okay, so after that, you're just gonna continue to turn the square. All right, turn the square, and you will get another flat line on top, but this time you already turn the square for 270 degrees, and this will be your third one. All right, and the last rotational symmetry will be, it's either you count it's either you start your rotational symmetry from the beginning, or you're just gonna count the first rotational symmetry when you start to turn. All right, in that case, the last rotational symmetry will be back to the original position, and this will be the number 4th rotational symmetry. And this is how you get the 4 rotational symmetries of any of the square. All right, and it can work on any shape. You can do a practice on yourself. I'm just gonna write a disclaimer at the side here. Square on the left have 4 rotational symmetry, but you need to ignore the dot, because if the dot I include in this square actually counts as the shape, there is only 1 rotational symmetry, because when you turn 90 degrees, the dot actually it's not producing the original square. Okay, do you get what I mean? If you don't get, please comment below and I will create another video explaining what I meant about this. In this video, the dot is just to let you see when how are you going to produce the same shape when you rotate the square. Okay, so after that, you're gonna see I can write, actually there are a few more most common one that you can see here. Are there any space down there? Okay, no. So the triangle, all right, you can do it as a practice yourself. Triangle, oh my gosh, this is ugly. The triangle have 3 rotational symmetry. Okay, and the circle, you can either say they have the circle has infinite, or I don't know whether 0 is counted, but I would say it's infinite. All right, and let's say a rectangle. A rectangle will only have 2 rotational symmetry, right? Why is it not 4 as the square? Because you can see that the longer flat line on top, when you turn 90 degrees, it will not produce. All right, when you turn it 90 degrees, all right, it will produce a shape like this, which is not the same as the original shape. Therefore, this cannot be counted as a rotational symmetry of a rectangle. So you need to turn another 90 degrees, which yields something like this. Then you can see these two are the same. Therefore, this is 1. And you turn another further 90 degrees, it's not. And at last but not least, it's the second rotational symmetry. All right, I hope you can see how to get a rotational symmetry by now. And there's a one last note down here. Any shape, okay, I'm gonna choose a darker color here. Okay, never mind, this one will do. Any irregular shape will have at least 1 rotational symmetry, because let's say there's a very weird shape right here that you cannot get any rotational symmetry by however you turn the shape. But you need to remember, when you turn 360 degrees and you get back the original position, that is counted as 1 rotational symmetry. Therefore, any shape will have at least 1 rotational symmetry. Okay, that's the conclusion. So after that, let us move on to line symmetry. Okay, what is a line symmetry? Line symmetry, okay. Line symmetry. Okay, line symmetry by its name itself suggests that you find the symmetry of a shape by drawing lines. Okay, so how do you draw lines? For example, the square from the previous example there. This is a square, okay? You need to never mind, I'll redraw this. This is a square. Okay, so line symmetry is when you draw a line, it will divide the shape into uh two same segments. Can I say that? Yeah. So how many line symmetry does a square have? Okay, so we can first try to divide this into half. This is definitely okay. Divide this into half. So you can get the left segment and the right segment is the complete same one. So this is 1, the first line symmetry. Okay, so if you're gonna do a dotted one to cut the square into the top and bottom, so this is the second line symmetry because it will yield the same area between the top and the bottom. The third one here, we're gonna cross it out from the diagonals. All right, so the top and the bottom, the top left and the bottom right will have this equal area here. Therefore, this will be another line symmetry. And last but not least, as you could have guessed, is this diagonal right here, which gives you the last line symmetry. Therefore, we can say a square, this is a square by the way, square has 4 line symmetry. Okay. From the same example here, oh yeah, I need to remind you that to look for line symmetry, you can actually imagine you are folding it so that you will get equal sides on both of them. Yeah, so when you fold it, so for example, right here, I have a rectangular piece of paper right here. So we're gonna use this example to find how many line symmetry there are in a rectangle. Okay, so let's first draw a rectangle. Okay, a rectangle. Yeah, please assume that's a rectangle. Yeah, okay, so first, if we're gonna fold the bottom, the top and the bottom, like this, okay, you can see that both sides are actually equal, all right? Both sides are equal. Therefore, this is the first line symmetry you can ever get for rectangles. So number 2, if you're gonna fold it to left and right like this, okay, I'm not sure if you guys can see it, like this, then you can see they are actually equal in area too. All right, there's no extra spaces for one side than the other. All right, so this is gonna be the second line symmetry. The question now is, can we draw the line from one diagonal to the other diagonal to get another line symmetry? All right, because as what I said just now, the line symmetry divides the shape into 2 parts so that both parts are equal. All right, so we can experiment this using this rectangle paper here. All right, if we're gonna fold the corners to the corners here, as you can see right here, these two shapes are not equal. All right, despite of them having the same area, but when you imagine it, when you actually have a rectangle paper here, you fold it, there are a lot more extra spaces right here, which means this is not a line symmetry for rectangles. So this is a very common mistake that a lot of people will do. So for a rectangle right here has only 2 line symmetry. All right, so this is something you need to remember. Okay, and I'm just gonna give a last example by saying this equilateral triangle. All right, we must say this is equilateral. Okay, equilateral triangle. Okay, so that all 3 sides are the same. Okay, and maybe after this equilateral triangle, I can give, okay, there's no more space. Okay, let me change the format here. Okay, so we have one equilateral triangle here. Okay, that's ugly. Just give me one more try. One equilateral triangle. Okay, equilateral triangle, and one isosceles triangle. All right, so the difference between an equilateral triangle and isosceles triangle is equilateral triangle have three same sides. All right, same sides, same three sides with the same length. Okay, and isosceles triangle there's only two, so this will be usually the shorter one. Okay, so both of them, although they are triangles, they have different line symmetry. So let's go with the equilateral triangle first. We can see if you have an equilateral triangle shape in front of you, you can try to fold it. All right. Uh, so the first one we can cut through the middle. All right, and it goes the same to all the from the corners to the middle opposite of them. All right. So this can show that equilateral triangle have only three line symmetry. But that's not the same case for isosceles triangle. All right. If you are gonna cut the isosceles triangle from the middle, from the corner between the two same length side, all right, to the middle, this is one line symmetry. However, you cannot do the same because you cannot do the same for the other corner there because from the left side and the right side, they are two different lengths. So when you cut through the middle, it will not produce the same area. Okay, if you have a isosceles shaped paper, or you can cut it up to try it and try to fold it, then you will not get the same size when you fold it. All right, so this gives a conclusion that for isosceles triangle there is only one line symmetry. Okay, so yeah, I hope you get all this rotational symmetry and line symmetry, and we're gonna move on to the angles. Okay, angles within the parallel lines. Okay, so from the last video we saw what is a parallel line. All right, so parallel lines have they have the same gradient and they never have intersection point. All right, so when you have two angles within parallel lines. Okay, when you have two parallel lines, all right, and you draw something like a, okay, these two are parallel, and you have like a kind of a line intersecting both of them. All right, there are some angle properties that you can actually see from here. Okay, so if you get a question asking you to look for angles, and you see the most often case you will see is two within two parallel lines. Okay, so the first one here is the alternate segment. All right, so the alternate segment is in, okay, I'm gonna write down first. Number one, alternate, actually it's not segment, alternate angles, I'll say. Alternate angles is in the form of Z. Okay, these two are parallel lines. Okay, so if you have an angle here called theta, this angle right here will be a theta. So the interior of a Z has the same angle. All right, so it's this part right here and this part right here. Maybe I'll just change some color when I color this. So the angle right here is the same as the angle right here. And this is called the alternate angles. All right, it's just that simple actually. You just need to remember these three different angles. So now we'll go on to the second one, which is called as the corresponding angles. Okay, so what is corresponding angles? Corresponding angles. Corresponding angles are angles So these two are parallel lines, and when you have a line crossing them, this two right here has the same theta. Okay, so this in turn means that if we move back to the main diagram here, and we are using a different color, let's say a lighter one, this angle right here is the same as this angle right here. And if you can kind of like see it visually, then these two angles actually have similar, have the similar angles because of one line cutting two parallel ones. Okay, so this is the second angle that you are going to learn today, corresponding angles. Last but not least, we have the co-interior angles. So as the name suggests, co-interior angles, all right, and usually I'll just call them interior angles, but it's better to write the whole name here. It's totally inside of the two parallel lines, all right? So these two. However, this time they are not the same angles, as you can see from the diagram. So we're going to name angle A and angle B. When both of them add up, they will be equals to 180 degrees. All right. So what is the theory behind this? Okay. So if we're going to say, what's the color that I use? And this color right here plus this color right here, okay, is equals to 180 degrees. So this part right here and this part right here is 180 degrees, right? Why can we deduce that? Okay, so from the previous video, if you remember, I said a straight line is 180 degrees. So if you can see from the top here, it's actually the same angles right here. So if you have the angle down here by alternate angle, you can say that it's the same right up here. And this is actually a straight line. So as you can see here, the darker orange with plus the lighter orange, or you can call it yellow, is equals to 180 degrees. It's just that simple. You don't actually need to memorize it. It's all by logic. Okay. So yeah, with this, we are done with the angles between parallel lines, and we're gonna move to the last part for the video today, which is to talk about interior angles. So let me write down interior angles. So what are interior angles? Interior angles are the angles within a shape. All right, so we are gonna start with a formula. All right, the formula for sum of, maybe use a different color, sum of interior angles is equals to 180 degrees multiplied with n minus 2, where n is equals to number of sides of the shape. All right, so if you are gonna say a square, okay, let's use square. Square has 4 sides. Therefore, the sum of the interior angles, I'm just gonna use it IA here because I'm just lazy, will be equals to 180 degrees multiplied with 4 minus 2. There you get 360 degrees. Okay, so you see how it works. So 180 degrees divided multiplied with n minus 2 is the sum of the interior angles. So if you can find the sum of interior angles, then you can find wait. Okay. If you can find the sum of interior angles, then you can find each interior angle will be equals to 180 degrees n minus 2 divided by n. Okay, so in this case, if we are talking about a square, so square, you have 360 degrees divided by 4, which gives you 90 degrees for each angle. All right, so you have 90 degrees at each 4 of the angles. All right, so this is how you look for sum of interior angles and the individual interior angle itself. So yeah, this is basically it. So uh, if you have something like a triangle, all right, so triangle have three sides. 3 minus 2 is 1, so 1 times 180 degrees is just 180 degrees itself. So the total interior angles in triangle is just 180 degrees, and it goes the same to all other shapes. And hopefully you will know by now, after quadrilateral it will be a pentagon, then it will be a hexagon, heptagon, octagon, and so on. So you can go on Google for this. I think I don't need to actually tell draw out all the sizes and the names itself. However, there's one thing that you need to take note here. The formula right here only works if only works for regular polygons. All right. So what do you mean by regular polygons? Regular polygons are, let's say, a square, it's a regular one. A triangle, it's a regular one. However, only equilateral triangle is a regular polygon. If it's isosceles triangle, then no, it's not. All right, so regular means you need to have same length sides same length for each side of the shape. All right, so if you see it's a regular, let's say regular pentagon, then each side will be 180 degrees multiplied with 5 minus 2, which is 3, which gives you 540 degrees for the total sum of interior angles, divided by 5, because 5 sides. Then you will get angle um for each side of the regular pentagon. So you need to make sure that you see the word regular before using this formula. However, the sum of interior angles work for regular and irregular ones. So if you just get a pentagon, but it's a very weird shape, very weird five-sided shape, you can still use this to get the sum of interior angles. All right. So the complement of this, which comes together with interior angles, are exterior angles. So what is exterior angle? Exterior angles. So by the name itself suggests that is the angle outside of the shape. So for example, if I'm going to draw a hexagon here, 4, 5, 6. All right, this is a hexagon. The exterior angle is this theta right here. For wait, this seems weird. Okay, wait. This theta right here, this theta right here, this theta right here, and so on. Okay. So all the exterior angles are same in length, same in size for regular polygons. Okay, and there is this formula right here. The sum. Okay, this is the notation for sum, the symbol for sum of exterior angles is equals to 360 degrees. Okay, so you can actually check with this hexagon right here. So as you can see here, we have 1, 2, 3, 4, 5, 6 exterior angles here. So we can write it as 6 theta is equals to 360 degrees, which gives you every single theta is 60 degrees. So every exterior angle is 60 degrees. So you might question, how do you get the formula? How do you make sure that the formula is correct? So we can prove it. So you can see, since this is a straight line, all right, which means anything inside this, let's name it alpha. So alpha plus theta is equals to 180 degrees because it's a straight line. So we are looking for alpha, which is 120 degrees. So from the previous slide, not slide actually, we have the formula for the sum of interior angles and the formula for each interior angle for regular polygons right here. So we can calculate each angle in a regular hexagon. Okay, so let's do it by saying each interior angle in a hexagon is equals to 180 degrees multiplied with 6 sides minus 2, which is 4, divided by the number of sides, which is 6, and therefore you will get 120 degrees. All right, so this proves that the sum of exterior angles is equals to 360 degrees is correct. Okay, and this is all for this exterior angle, and in fact this is all for this video. So let's have a recap on what we did in this video. Number one, I had introduced to you rotational symmetry. All right, you can try it out with a lot of different shapes. But remember, if you have an irregular shape that you cannot find any similar ones when you rotate through the 360 degrees, there is always one rotational symmetry. All right. However, it's a different case for line symmetry. If you have an irregular shape that you cannot divide into half by at any place, then there can be zero line symmetry. All right. Next, we have learned 3 different angles within parallel lines, the alternate, corresponding, and co-interior. And yeah, this is basically just memorizing work, although you can just derive it. Okay. Next, we have interior and exterior angles for regular and irregular shapes. So I hope you guys understand all the information covered in this video today. And yeah, I'll see you guys in the next video. Thank you.